activities 4A and 4B. Both are both parts are about sounds made by vibrating air, so different air columns. So in the first, for activity 4A, the first thing students do is they take a straw, cut it in half, then take that half, cut it in half, and then take that and cut it in half. So you end up with an eighth, a fourth, and half a straw. And then you blow across the top of the straws and listen for the different pitches. So this is the straw that is 1/2. This is what it sounds like. That's 1/2 of the length of the full straw. Okay, a quarter. And then the straw length that is 1/8 of the normal straw. And what you hear is, as the straw gets shorter, the pitch gets higher. So again, in order from longest to shortest. Okay, so you can hear the difference in that. And then you were asked to cover one end of the straw and listen to the difference in the pitch when the straw is covered and when the straw is uncovered at one end. So here is covered at one end. And here is uncovered. So it's supposed to be able to figure out which one produces the highest pitch, which covered or uncovered. So again, this is covered and uncovered. And you should be able to tell that uncovered, so open, a straw open at both ends, is going to produce a higher pitch. So if we're looking at these questions, the shorter the piece of straw, both ends are open, then the higher the pitch. Shorter is always going to produce a higher pitch. As you uncover the bottom of the straw, the pitch increases. So you were supposed to read the physics talk section on page 521 and 523 and answer the questions. So the sound produced was a standing wave in the straw. Standing wave in the straw, the air in the straw, and then it travels to your ear as a longitudinal wave. But the sound produced was a standing wave. 4, do the air molecules at both ends move back and forth if both ends of the straw are open? That would be yes. And 5, if the straw is open at both ends, how much of the standing wavelength fits inside? If it is open at both ends, it's going to be 1/2 of the actual wavelength. Number 6, do the air molecules vibrate at the covered end of the straw? No. The pressure gets built up. There's no room for the air to vibrate back and forth because the pressure builds up because that end is closed. So if the straw is closed at one end, how much of the standing wave fits inside? If it is closed, if the straw is closed at one end, then 1/4 of the wave actually fits inside. The ability of sound waves to spread out as they pass through an opening is called diffraction. So you were asked to draw the tubes as shown on page 523 in the label your drawings. So the top one shows a straw that is open at both ends. So when you blow across one of the open ends, then the air inside is going to vibrate, and you're going to end up with half of the wavelength inside the straw. If the straw is closed at one end, like the example on the bottom, then you end up with 1/4. So if we said that if our straw is, we'll say 10 centimeters, then we can figure out the actual wavelength, because if half fits inside, then we need 2 halves to make a whole. So our 10 centimeter straw, multiply that by 2, and we're going to end up with a wavelength of 20 centimeters. So if the tube is closed at one end, then 1/4 of the wavelength is inside the straw. So it takes 4 to make a hole, 4/4 to make a hole. So it would be our 10 centimeters. We're assuming our straw is the same length. So from here to here is 10 centimeters. So we would do 10 centimeters times 4, and that would give us a wavelength of 40 centimeters. So if you're looking at wavelength, shorter wavelength is going to produce a higher pitch. So the open straw, this is why the open straw that's open at both ends is going to produce a higher pitch. It's a wavelength of 20 centimeters versus closed at one end, which would produce a wavelength of 40 centimeters. So shorter wavelength, higher frequency. So activity 4B, you continued with air columns, sounds and air columns, and you were to take 2 or 4 test tubes. You left 1 test tube empty. You filled one 1/4 of the way full, another one half full with water, and then another one 3/4 of the way full with water. And again, blow across the top of the test tubes and listen to the sounds and figure out the highness or lowness of the pitch based on the amount of water in the test tubes. So we'll start with an empty test tube. So this is, I'm trying to see if I can make it produce the sound with the test tube. So that is with an empty test tube, so pretty low pitch. This is the test tube that is 1/4 of the way full. Okay, so 1/4 of the way full, and this is back to the empty. So here's the test tube. Here's the pitch made by a test tube that's half full. And the test tube that is 3/4 full. Okay, so finally, so that's pretty good. So, and again, you should have noticed that as the air column gets shorter, the pitch produced gets higher. So the next part, you were supposed to sketch the empty test tube, quarter full, half full, and then 3/4 full. The actual air column length, so you measured the length of in the test tube that did not have any water in it. So the first time for the empty test tube, you measured, it should have been about 12 centimeters. We need to convert to meters. So we would do that by moving the decimal 2 places to the left. So you have 12, it's 12 centimeters, so we'd move our decimal 2 places to the left. So it would be 0.12 meters. The 3/4 full would be about 0.08, 0.06, actually that's 0.09, 0.06, and then 0.03 meters for 3/4 full. So as you can see, as you're going down, as the air column's getting shorter, then the pitch was getting higher. So then you had to calculate the wavelength, okay? And again, the air column is closed at one end, so you have to, so a quarter of the wave is actually produced, that actually fits inside the air column. So you multiply by 4 to get the actual wavelength. So 0.12 times 4 would give you 0.48. And then do the same thing for the other 3 air columns. So 0.09 would give you 0.36. 0.06 times 4 would give you 0.24. And 0.03 times 4 would give you 0.12. So that is how you figure out the actual wavelength produced by the air column. So then we're going to figure out the frequency, okay? So here's what we know. We know that sound, the speed of sound in air is about 340 meters per second. And we know the wavelength. So to calculate the frequency, then we need to take our wave speed. So frequency equals wave speed divided by the wavelength, okay? So 340 divided by 0.48 would give us 708. 340 divided by 0.36 is going to give us 944, frequency of 944. 340 divided by 0.24 give us 1,400, and we'll round to 17 hertz. And then 340 divided by 0.12 would give us a frequency of 2,833. So again, if you compare this column, well, all 3 columns, okay, if you look at them. So as our air column length gets shorter, then our frequency is increasing, okay? As the wavelength gets shorter, then our frequency increases. And frequency, remember, is how many vibrations that happen every second. So low frequency, low pitch, high frequency, high pitch. So for the summary, the longer the air column in the test tube, the longer the air column, the lower the pitch. As the air column length decreases, the pitch increases. So as your air column length shortens, the pitch is going to increase. So the more water in the test tube means you have a shorter air column, so you're going to have a higher pitch. And then you were asked to answer some questions regarding air columns. So sound travels as a compressional or longitudinal wave. the molecules of air bunch up or spread apart as sound passes by. The air moves back and forth, and the wave moves across the room. That's true. The energy moves, the molecules stay put. The shorter tube, the shorter the wavelength. The shorter the wavelength, the higher the pitch. The ability of sound waves to spread out, we've talked about that before, is diffraction. The smaller the opening, the more that waves spread out. And then why does a piccolo have a higher frequency than a bassoon? Because a piccolo is shorter than a bassoon. And if you don't know what a bassoon is or what a piccolo is, you still know that a shorter air column is going to produce a higher pitch. So a piccolo has a higher frequency and produces a higher pitch because it is shorter than a bassoon.